Hello everyone. In this video, we go through the Poisson solver with background charges. The main objective of this simulation aims to solve Poisson equation for a nanowire quantum dot device while incorporating the effect user-defined background charges under cryogenic condition. Especially, this simulation aims to understanding the impact of interface charges, enhance understanding of charge trap modeling, and investigating the effect of localized volume charges and applied adaptive machine for conversion. Technology is a distributor of next generation technology simulation software like in nanotechnology, nanomaterial, solar cell, organic LED, and lot more. And we are partner with three companies. First one is Nano Academy. Nano Academy is a Canadian based company which will offer some software like first one is Nanotical. In Nanotical, you can perform the modeling and simulation of nanoelectronics, nanowire, and nanomaterial like a carbon nanotube, spintronics device, solar cell, and lot more. Second one is Rescue. In Rescue, you can perform modeling and simulation of large-scale DFT, nanomaterial, and nanoelectronics. You can study on electronic structure, crystal structure, device builder, lattice parameter, nanowire, nanotube, and third one is QTCAT. We will know more about QTCAT in upcoming slide. Second company is Fluxim. Fluxim is a Switzerland-based company which provides world-class software and hardware for photovoltaic device, tandem, thin film, and organic, and light emitting diode, quantum diode, LED, OLED. And third company is Metra. It is a cloud-based material simulation software. Talking about our services, we are software distributor of next generation technology simulation software, training program with our experts. We provide technical support also, and we offer some equipment like Provi station, sample holder, battery tester, and recycler strip. And our valuable customer are top pioneer institute of India such as IIT Madras, IIT Guwahati, SRM Institute, and lot more. To the simulation part, a small introduction about cryogenic temperature, nanowire, charges, and solver being used in this simulation. Imagine a nanowire, a thin wire at 10 nanoscale surrounded by an insulating oxide. These wires form the backbone of cutting edge technology like quantum computing and ultra fast transistor. But what happens when charges either on the surface or inside the oxide interface with wire? That exactly what we will explore using QTCAT. Talk about nanowire. A nanowire is a super tiny one-dimensional structure. Think of it like an extremely thin wire with a diameter in the range of 1 to 100 nanometers. Material of nanowire can be made from various material like semiconductors such as silicon or gallium arsenide, metal or even insulating material. Property of nanowire is high aspect ratio. This means nanowire are very long compared to their width. Imagine a very thin long thread. This property makes them perfect for tiny devices. Quantum confinement. In nanowire, electrons are confined in two dimensions, leaving only one dimension for them to move freely. This is like having a narrow halfway where people can only move forward or backward. Poisson equation. This is a mathematical equation that helps us understand how electric charge are distributed in a material. It is a crucial for designing semiconductor and other electronic components. If we talk about cryogenic temperature, this refers to a very low temperature, often close to absolute zero. At this temperature, the behavior of charge and electron changes, which can make simulation and experiment more complex. When we talk about mesh, a mesh is like a 3D grid we put over our device. Regular meshes use the same size grid everywhere, but this is an inefficient method. Some area need more detail than other. Now you might wonder, why do we need adaptive meshing? Well, when we try to solve Poisson equation, especially at very low temperature like near absolute zero, the traditional method can struggle. Consider an analogy. Imagine trying to find your way through a dense forest.
If you have detailed map only for the clear path, you might get lost in the thickest. Adaptive meshing helps us create a more detailed map where we need it most. Adaptive meshing allows us to refine our mesh the area where the electric potential changes rapidly. We start with a coarse mesh and then refine it based on where we see significant change in potential. This means we can focus our computational power where it really needed. If you look at the left diagram, it is a normal mesh with same size grid everywhere. It misses critical variation in potential. In second image, adaptive meshing start with coarse mesh, then automatically refine area where electric potential changes rapidly. To use this technique, we typically need some software tools like QTCAD and GMesh. These tools help us to create and manipulate our geometry file. We are diving into an exciting topic: how background charges affect the behavior of nanowire devices. We will explore two types of charges: surface charge density at the interface and Gaussian shape volume charge inside the oxide. Let's get started. These charges can be introduced in two main ways: at the interface between material and within the oxide layer. Understanding their impact is crucial for designing better electronic devices. First, let's talk about surface charge density at the interface. Imagine the boundary where the semiconductor channel meets the surrounding oxide layer. In real devices, the interface can trap charges known as charge trap. These trap capture electron or holes and affect the current flowing through the channel. To model this, we add a constant negative charge on the surface. This helps us understand how these traps impact the device behavior. For example, they can create potential barrier or alter the electric field, affect the overall performance. Next, let's look at a volume charge inside the oxide layer. Sometimes individual defect or impurity can change the property of the oxide. To model this, we introduce Gaussian shaped volume charge, which is shaped like a bell curve and is placed exactly in the middle of the channel. This charge distribution help us simulate the impact of a single defect or impurity. These impurities can affect the electric field and overall device performance, making it essential to understand their behavior. Modeling these background charges is crucial for several reasons. First, it helps me understand how real-world devices behave. Second, it allows us to design better device by accounting for these effects. By simulating the impact of a surface and volume charge, we can optimize the performance of a nanowire device. In the world of nanotechnology, understanding how background charges affect device is crucial. These charges can exist at the interface between material or within the material itself. Let's break down the two charge model and see how they help us simulate real world scenario. First up, the surface charge model. This model helps simulate situation where many small charge traps exist at the interface between the semiconductor and the oxide layer. These traps are common in real devices, can affect how the transistor turns on or off. By adding a constant negative charge on the surface, we can simulate these traps and understand their impact on device behavior. This is essential for designing more reliable and efficient devices. Next, let's look at the volume charge model. This model represents a single impurity or charge trap inside the material which can disturb the electric field. Gaussian functions are commonly used here because they smoothly distribute the charge around the center point. By simulating these volume charge, we can understand how individual defects or impurity affect the device performance. This is crucial for optimizing the design of nanowire devices. So, why are these models important? They allow engineers to predict how real-world imperfections like charge trap affect device performance. By adding these user-defined charges, we can simulate different scenarios and design more reliable devices. Let's see how these charges affect the device. We will run simulation with and without background charge and compare the result. This will give us a clear picture of their impact on conduction band edge and overall device performance. QTCAD allows us to model this charge distribution accurately and understand their effect on device performance. This is essential for advancing the field of nanotechnology and designing the next generation of electronic devices. The process of the simulation is first we use QTCAD software for the simulation. First step is to create the geometry of the device where we define the shape, dimension of the device geometry with a name nanowire background charges 0, which will create a mesh file where computational occurs. After that, we create Python script where QTCAD modules are, are imported, like we define where device material and boundaries. After that, we define background charges like surface charge at the silicon and silicon dioxide interface, Gaussian volume charge. And after that, we use Poisson solver where you use adaptive meshing with 20K node and do solver with and without background charge for a comparison. After that, we evaluate the result. In this section, you will learn about QTCAD workflow. Let's break down the different stages and component. First step is device specification. The first step in the workflow involves selecting the technology and defining the device specification. In this case, the technology being used is nanowire. This step allows you to design an arbitrary 3D geometry of the device, meaning you can configure the shape, dimension, and material used in transistor. This step is crucial because it defines the foundation of the entire simulation. The accuracy of the result will depend on how well the device geometry is specified. And the second step is mesh definition with GMesh. The second step is the creation of the mesh, which is representation of the device symmetry in smaller elements. A mesh is essential, a grid that divides the device into smaller, manageable sections. This is important because the Poisson solver and other numerical solver work on these small sections to calculate electrical properties like potential and charge distribution. This process is known as meshing, and final mesh provide more accurate results, especially in areas where the electrical potential changes rapidly. However, final mesh also require more computational power. And the third step is running the QTCAD software. QTCAD also comes with inbuilt quantum models and material, which means it's already includes certain material and quantum effect relevant to the nanowire. This step run the heavy lifting computation and the flexibility of the Python API allow user to fine-tune their simulation and adapt them for various scenarios. And the fourth step is visualization and analysis. The final step involves visualizing the result of the simulation for analysis. The result of the simulation can be visualized tool like PyPlot, PyVista, or Parabola. The simulation part, as you remember from the workflow of QTCAD, the first step is to create geometry of the device, where we can define shape, dimension of the geometry of the device. I created earlier with name nanowire background charges.go file. Let's open with GMesh software. I store in the QTCAD folder, example folder, then tutorial, then meshes. We'll look at the geometry. It has two concentric cylinders, and the inner cylinder is filled with silicon, and the outermost cylinder is silicon dioxide, and the outermost layer is metal, and the one end is source, and the other end is drain. And it has created two mesh files, which has named Geo Unrolled and MS4 file stored in the meshes folder. This file nano background charges CO unrolled file and nano background charge mesh file. The creation of geometry and mesh file. Now it's time to where QTCAD comes, where we define material, device parameter, solver, plot band. Let's jump to the Python script. Created background charges.py Python script where we import some necessary library and defining some device parameter. First, import path lib for handling file system path. After that, we import numpy as a np for numerical operation. From copy, import deep copy for creating
deep copies of object. After that, matplotlib, pyplot for plotting graphs. From QTCAD device constant for physical constant used in the simulation. Mesh 3D for handling 3D mesh data. QTCAD device analysis for analyzing simulation result. Material for defining material properties. Device for creating and managing device object. Poisson for solving Poisson equation. After importing some important model, now it's time to define some device parameter. VGS is gate source voltage, which is 2 volt. After that, we define Butterworth function, which is the sum of electron affinity and the half of electron band gap. After that, we define device height in nanometer and device radius in nanometer. In the next section, we define some background charges parameter. Surface charge density. Surface charge density is set to negative charge. After that, volume charge. Total charge in the background. Volume charge density is set to minus 5 times the elementary charge. After that, volume charge spread. Spread deviation to the Gaussian charge density set to 1 nanometer. After that, we define path to the mesh file and output file. Script directory is the file containing the script, and the path to the mesh file. After that, path is used for the geometry file, and after that, we load the mesh, which is scaling in nanometer, and mesh file with the mesh object created from the mesh file. After that, we create device and set temperature to 10 millikelvin. In this section, we create a region of the device, create with dot new region with material silicon dioxide in channel oxidation, source ox and drain ox for the silicon dioxide. After that, we define a device dot new region for channel, source and drain, where you use material silicon, and in drain and source we use p-doping concentration and n-doping is 0. After that, we create boundaries with name, source band, drain band, and gate band, where a gate source voltage defined and Butterworth function. Device no charge deep copy. This line create a deep copy of the device object without background charge for comparison. After that, we add surface charge at interface between silicon channel and silicon dioxide. Basically, this line add a surface charge density at the interface between the silicon channel and the silicon dioxide. In this section of code, this line define a Gaussian shaped volume charge density in silicon dioxide. Here x, y, z coordinate for the center of a Gaussian distribution, and Gaussian x, y, z function defining the Gaussian charge density. After that, we use device set volume charge density. Set the volume charge density using the Gaussian function. Configure the nonlinear Poisson solver. In first, we define the solver parameter object. After that, we set the tolerance and an initial reference factor. After that, final reference factor and minimum nodes. After that, this section create adaptive mesh nonlinear Poisson solver object for both devices. SLV is solver for the device with background charges, and SLV no charge means solver the device without background charges. Here he used self-consistent solution for each device without background charge and with background charges. This section evaluate the conduction band edge along the line cut for comparison, like Z band edge Z line cut along the symmetry axis of the nanowire for the device with background charges, and Z no charge band edge is used for line cut along the symmetry axis of the nanowire for the device without background charges. After that, line cut along y-axis. Y band edge line cut along y-axis for the device with background charges, and after that without background charges. After that, in this section produce plot of the line cut for a comparison. In the last section, we plot charge density in device with background charges along slices. Let's run the code. Exploded the mesh file with some 3D mesh statistics and solving Poisson equation with the bond, and some Poisson iteration happen to solve converge on mesh file with fewer nodes that minimum. See minimum node parameter, relative error and error threshold, and load refined mesh. Again some Poisson iteration happen. Loaded the band diagram with and without background charges along z-axis and along y-axis. and explored the charge density.
Before moving, there you have it. We have explored how the surface charge model and volume charge model help us understand and simulate the impact of background charges on nanowire devices. By using this model and tool like QTCAD, we can design more reliable and efficient electronic device. Thank you.